The 20th century produced machines so large, costly, and extreme that their very existence bordered on excess. Born from war, fear, and rapid technological change, these mega-machines were often conceived to solve urgent strategic problems that vanished almost as quickly as they appeared. Some were completed just as doctrine shifted. Others proved politically or economically impossible to sustain, and a few worked exactly as intended but arrived too late to matter. What unites them is not failure of engineering, but failure of timing. These projects reveal moments when ambition outran practicality, and when history turned faster than steel, reactors, or concrete could keep up. Each of these machines briefly stood at the edge of what was possible, then was left behind almost as soon as it was built. The Hughes H-4 Hercules, Spruce Goose, the largest flying boat ever built that flew once. The Hughes H-4 Hercules, more commonly known as the Spruce Goose, was the largest flying boat and one of the most ambitious aircraft ever constructed. Its origins lay in 1942, when the United States faced severe shortages of steel and aluminum due to wartime demands. Industrialist and aviation pioneer Howard Hughes proposed an enormous wooden transport aircraft capable of carrying troops, vehicles, and supplies across the Atlantic while avoiding German U-boat threats. The project was formally designated HK-1, reflecting the partnership between Hughes Aircraft and the Kaiser Shipbuilding Company. The aircraft was designed almost entirely from laminated birch, not spruce as the nickname implied, using a process called Duramold that bonded thin layers of wood under heat and pressure. After Henry Kaiser withdrew from the program in 1944, due to disagreements over cost and schedule, Hughes continued development alone, redesignating the aircraft as the H-4 Hercules. By that time, the strategic need for the aircraft had already diminished, but Hughes persisted, driven by personal conviction and reputational stakes. The H-4 was unprecedented in scale. It featured a wingspan of 97.5 meters, longer than any aircraft that would fly until the AN-225 decades later. The aircraft was powered by 8 Pratt & Whitney R-4-360 Wasp major radial engines, each producing 3,000 horsepower. At maximum configuration, it was designed to carry over 68 metric tons of payload, including up to 750 fully equipped troops or heavy military equipment. The hull was configured as a flying boat, allowing operations from open water rather than conventional runways. Political scrutiny followed the project closely. In 1947, Hughes was summoned before the U.S. Senate War Investigating Committee, accused of wasting public funds on an aircraft that many believed would never fly. In response, Hughes publicly committed to demonstrating the aircraft's airworthiness. On November 2, 1947, during taxi tests in Long Beach Harbor, Hughes unexpectedly advanced the throttles and lifted the H-4 into the air. The aircraft flew approximately 1 mile at an altitude of about 21 meters, remaining airborne for roughly 26 seconds. Although the flight proved the aircraft could fly, it did not save the program. The H-4 never flew again. Jet aircraft and conventional transports had rendered its mission obsolete, and the cost of further testing could not be justified. Hughes retained the aircraft in climate-controlled storage for decades, personally funding its preservation until his death in 1976. Today, the H-4 Hercules stands as a monument to wartime ambition and individual obsession. It was not abandoned due to mechanical failure, but because the world moved on before it was ready. The Spruce Goose flew once, just enough to prove its creator right, and then passed immediately into history. Project Habakkuk, the ice aircraft carrier that melted out of history. Project Habakkuk was one of the most bizarre, yet technically serious military proposals of the Second World War, envisioning an aircraft carrier built primarily from ice. The concept emerged in 1942, when Allied shipping losses to German U-boats in the Atlantic reached critical levels. Britain lacked sufficient steel, shipyard capacity, and long-range air cover to protect convoys in the mid-Atlantic gap. In response, British scientist Geoffrey Pike proposed an unconventional solution: enormous floating airfields made from ice, capable of operating aircraft far from land bases. The project was taken seriously at the highest levels. Prime Minister Winston Churchill personally approved exploratory funding, and responsibility for evaluation was assigned to the Combined Operations Headquarters. The material at the heart of the concept was pykrete, a composite of ice mixed with approximately 14% wood pulp. Pykrete proved far stronger than ordinary ice, resistant to melting, and capable of absorbing ballistic impacts without shattering. Tests showed it could stop bullets and resist cracking under stress, making it theoretically suitable for large-scale naval construction. Design studies envisioned a vessel of staggering proportions. Proposed Habakkuk carriers would measure over 600 meters in length, with a displacement exceeding 2 million tons, dwarfing any ship ever built. The hull would be refrigerated internally to prevent melting, requiring an extensive network of cooling pipes powered by onboard machinery. The flight deck would support dozens of aircraft, while the thick pykrete structure would make the vessel nearly unsinkable by torpedoes or bombs. In theory, even severe damage could be repaired by refreezing sections of the hull. To test the feasibility, a small-scale prototype was constructed in 1943 on Patricia Lake in Alberta, Canada. The experimental structure validated many of the material properties, but also exposed serious limitations. Maintaining structural integrity required constant refrigeration, increasing power demands and complexity. Construction time was measured in years rather than months, and the sheer scale of the project posed unprecedented logistical challenges. 1944, strategic circumstances had changed. Long-range aircraft such as the B-24 Liberator closed the Atlantic air gap. Escort carriers entered service in large numbers, and U-boat losses mounted. Steel shortages eased, and conventional solutions proved faster and cheaper. The projected cost of Habakkuk rose dramatically, while its military advantage diminished. Project Habakkuk was formally abandoned before full construction began. Although never completed, it remains a striking example of wartime desperation driving radical engineering. Built around sound scientific principles, it was ultimately undone by practicality. The ice carrier did not fail because it was impossible, but because the war moved faster than the idea itself. The Northrop YB-49, America's jet flying wing, killed by politics. The Northrop YB-49 was one of the most advanced bomber concepts of the immediate post-Second World War era, representing a radical departure from conventional aircraft design. Its origins lay in the earlier YB-35, a propeller-driven flying wing developed by Northrop during the 1940s under the leadership of aircraft designer John K. Northrop. The flying wing promised lower drag, greater range, and higher payload efficiency by eliminating the fuselage and tail entirely. When jet propulsion matured near the end of the war, the U.S. Army Air Forces ordered a jet-powered variant, which became the YB-49. The first YB-49 prototype flew on 21 October 1947. Powered by 8 Allison J-35 turbojet engines buried within the wing, the aircraft demonstrated impressive speed and altitude performance for its time. It could reach speeds approaching 800 kilometers per hour and operate at altitudes above 12,000 meters, rivaling early jet bombers. The smooth, tailless flying wing also exhibited a naturally low radar cross-section. Decades before, stealth became a formal design discipline. Despite its promise, the YB-49 suffered from serious technical challenges. Stability and control were major issues, as the absence of a vertical tail made yaw control difficult, particularly at low speeds. The aircraft relied on split drag rudders and complex control inputs, which pushed the limits of human pilots without the benefit of modern fly-by-wire systems. Navigation and bombing accuracy were also problematic, as the aircraft's motion made precise targeting difficult with existing analog equipment. The program suffered a major setback in June 1948 when one of the prototypes crashed during a test flight, killing its crew, including Air Force Captain Glenn Edwards, after whom Edwards Air Force Base was later named. Although investigations did not condemn the basic concept, confidence in the aircraft was shaken at a critical moment. Politics and institutional rivalry ultimately sealed the YB-49's fate. In 1948 to 1949, the newly independent U.S. Air Force committed to the Convair B-36 Peacemaker as its primary intercontinental bomber. The B-36, though slower and technologically conservative, offered longer range, greater payload, and lower perceived risk. Secretary of the Air Force Stuart Symington canceled the flying wing program in early 1950, ordering remaining airframes scrapped. John Northrop later claimed that political pressure and industrial favoritism played decisive roles in the cancellation. While those claims remained debated, the outcome was clear. The YB-49 was abandoned, just as jet technology and electronic controls were on the verge of catching up to its design philosophy. Decades later, Northrop's flying wing concept re-emerged in the B-2 Spirit stealth bomber, vindicating many of the YB-49's principles. The aircraft was not abandoned because it was wrong, but because it arrived too early and challenged entrenched interests. Its cancellation stands as one of the most consequential lost opportunities in American aviation history. The Soviet T-15 tsunami torpedo, a weapon so big it was never fired. The Soviet T-15 torpedo was one of the most extreme nuclear weapons concepts of the early Cold War, conceived at a time when delivery systems for thermonuclear warheads were still limited and unreliable. The idea emerged in 1950, shortly after the Soviet Union's first atomic test, when planners sought unconventional methods to threaten the United States directly. The proposal envisioned a gigantic nuclear torpedo capable of destroying coastal cities with a single detonation, bypassing air defenses and missile interception entirely. The intellectual origin of the T-15 is closely associated with physicist Andrei Sakharov, who was involved in early Soviet thermonuclear weapons development. Sakharov suggested that a very large nuclear charge detonated underwater near an enemy coastline could generate massive blast effects and radioactive contamination. The concept was not primarily about a literal tsunami, as later myths suggested, but about delivering an overwhelmingly destructive underwater nuclear strike against ports and naval bases. Technically, the T-15 was unprecedented. The torpedo was designed to be approximately 23 meters long and over 1.5 meters in diameter, far larger than any operational torpedo before or since. Its estimated weight exceeded 40 metric tons. Because no existing submarine could accommodate such a weapon, an entire submarine class was effectively designed around it. Early Project 627 nuclear submarine designs included a single bow-mounted launch tube exclusively for the T-15, sacrificing conventional torpedo armament entirely. The warhead itself was projected to have a yield of up to 100 megatons, comparable to the later Tsar Bomba test of 1961. Such a detonation would have devastated any coastal installation within range and rendered large areas unusable due to radioactive fallout. However, the delivery method introduced severe practical problems. The torpedo's range was limited, forcing the launch submarine to approach dangerously close to enemy shores. Escape after launch was doubtful, making the weapon effectively suicidal for its crew. By 1954, serious objections emerged within the Soviet Navy. Admiral Nikolai Kuznetsov and other senior officers criticized the T-15 as tactically useless and strategically inflexible. They argued that submarines armed with standard torpedoes and emerging ballistic missiles offered far greater versatility and survivability. At the same time, progress in missile technology rapidly reduced the perceived need for such an extreme device. In 1955, the T-15 project was formally canceled before any operational weapon was built. Submarine designs were revised to carry conventional torpedoes and later submarine-launched ballistic missiles instead. The concept briefly resurfaced in later discussions about underwater nuclear weapons, but never again at such scale. The T-15 remains a symbol of early Cold War thinking, when the boundaries of destruction were still being explored without restraint. It was abandoned not because it was impossible, but because it was too large, too dangerous, and too impractical even by the standards of nuclear deterrence. The Lockheed CL-1201, the nuclear-powered aircraft that never left the drawing board, then was dropped. The Lockheed CL-1201 CL-1201 was one of the most extreme aerospace concepts ever seriously studied by the United States, representing the final and most exaggerated expression of Cold War nuclear-powered flight. Developed during the mid to late 1960s, the CL-1201 was not a prototype or experimental aircraft, but a detailed engineering study conducted by Lockheed as part of broader U.S. Air Force and Atomic Energy Commission interest in nuclear propulsion. Its purpose was to explore whether an aircraft of unprecedented size and endurance could remain airborne for weeks while serving as a mobile weapons and command platform. The concept envisioned an aircraft powered by a nuclear reactor driving conventional turbofan engines, eliminating the need for chemical fuel for cruise flight. The proposed design was staggering in scale. The CL-1201 would have had a wingspan of approximately 340 meters, more than 4 times that of a Boeing 747, and a maximum takeoff weight exceeding 5,400 metric tons. Crew estimates ranged from 20 to 30 personnel, supported by onboard living quarters, rest areas, and mission control spaces. Endurance projections suggested continuous flight durations measured in weeks rather than hours. Lockheed studies proposed several mission variants. One version was designed as an airborne aircraft carrier, capable of carrying and launching dozens of parasite fighters from internal bays. Another variant focused on strategic deterrence, acting as a persistent nuclear strike and command platform armed with missiles. A third configuration emphasized early warning and communications relay roles, remaining aloft indefinitely to survive a first strike and coordinate retaliation. Despite the ambitious vision, the technical and political obstacles were overwhelming. Nuclear propulsion required massive radiation shielding to protect the crew, which dramatically increased weight and complexity. Any accident, even a conventional crash, risked dispersing radioactive material over wide areas. The aircraft would have required specially reinforced runways and dedicated infrastructure that did not exist anywhere in the world. Maintenance, emergency procedures, and crew safety protocols posed unresolved challenges. By the late 1960s, strategic priorities shifted decisively away from nuclear aircraft. Intercontinental ballistic missiles, ballistic missile submarines, and satellite-based systems provided more reliable and less controversial deterrence. At the same time, public and political opposition to flying nuclear reactors intensified, influenced by earlier nuclear aircraft experiments such as the Convair NB-36H. Advances in aerial refueling further reduced the need for extreme endurance platforms. The CL-1201 was quietly dropped without formal cancellation, remaining confined to concept art, wind tunnel data, and internal reports. It was abandoned before construction not because it lacked imagination, but because it exceeded every practical boundary of cost, risk, and necessity. The Lockheed CL-1201 stands as a reminder that Cold War engineering sometimes pushed far beyond what strategy, safety, or reality could support. The FV4005 Stage 2, Britain's giant gun tank with no battlefield role. The FV4005 Stage 2 was one of the most extreme armored fighting vehicles ever constructed by the United Kingdom, designed during the early Cold War when tank firepower was rapidly escalating in response to heavier Soviet armor. The project originated in the early 1950s, as British military planners sought a means of defeating emerging heavy tanks such as the Soviet IS-3 without developing an entirely new main battle tank. Instead, the solution was to mount an extraordinarily large gun on an existing chassis, prioritizing raw destructive power over practicality. The FV4005 program was based on the Centurion tank platform, which was already the backbone of British armored forces. The Stage 2 variant was armed with the 183mm L4 gun, the largest tank gun ever fitted to a fully enclosed turret. This weapon was originally developed to fire high-explosive squash-head ammunition capable of defeating even the thickest armor through shock transmission rather than penetration. The gun's recoil forces were immense, requiring extensive structural reinforcement and imposing severe limitations on ammunition handling. To accommodate the weapon, engineers designed a massive, box-shaped turret that bore little resemblance to conventional armored designs. The turret was extremely tall, thinly armored, and offered minimal protection against enemy fire. Only 12 rounds of ammunition could be carried, and loading required significant crew effort due to the size and weight of each shell. The silhouette of the vehicle made concealment nearly impossible, and its height rendered it vulnerable to artillery, aircraft, and anti-tank weapons. The FV4005 Stage 2 was completed and tested around 1956. Firing trials demonstrated that the 183mm gun was devastatingly powerful, capable of destroying any tank then in existence. However, the tests also highlighted fundamental flaws. Accuracy was limited, rate of fire was extremely slow, and the vehicle's overall combat survivability was poor. The Centurion chassis struggled under the added weight, and the turret design offered no realistic protection in a modern battlefield environment. At the same time, tank warfare doctrine was changing rapidly. Guided anti-tank missiles, improved kinetic penetrators, and more balanced main battle tank designs made single-purpose gun platforms increasingly obsolete. Britain had already explored a more practical application of the same gun on the FV-215B, but even that concept was quickly overshadowed by missile technology. As a result, the FV4005 Stage 2 was never adopted for service. Only a single prototype was built, and the project was quietly abandoned without entering production. Today, the surviving vehicle is preserved at the Bovington Tank Museum, where it stands as a striking example of Cold War experimentation. The FV4005 was not abandoned because it failed to work, but because it solved a problem that no longer existed. It represented the final extreme of gun-based anti-tank thinking, rendered irrelevant almost as soon as it was completed. The Convair NB-36H, the nuclear reactor aircraft nobody dared arm. The Convair NB-36H was one of the most unusual aircraft ever flown by the United States, serving as a test bed for nuclear-powered flight during the early Cold War. Its origins lay in fears during the late 1940s that conventional bombers might soon lack the range and endurance needed to penetrate Soviet airspace. In response, the U.S. Air Force and the Atomic Energy Commission initiated the Nuclear Energy for the Propulsion of Aircraft program, commonly known as NEPA, to explore whether nuclear reactors could power long-range strategic bombers. The NB-36H was derived from the massive Convair B-36 Peacemaker, the only aircraft large enough to realistically carry a nuclear reactor and its associated shielding. Modified airframes were designated NB-36H, with the first flight of the nuclear test aircraft occurring in 1955. Importantly, the reactor carried on board did not power the engines. Instead, the aircraft remained conventionally powered by 6 Pratt & Whitney R-4 piston engines and 4 General Electric J-47 turbojets. The reactor's sole purpose was to study radiation behavior, shielding effectiveness, and operational safety during flight. The nuclear reactor installed aboard the NB-36H was a compact air-cooled unit housed in a reinforced bay behind the cockpit. To protect the crew, engineers installed a heavily shielded flight compartment using lead, rubber, and polyethylene, creating a cockpit weighing over 11 tons. Additional radiation sensors were distributed throughout the aircraft to collect data during operation. In the event of an emergency, the reactor was designed to be jettisoned by parachute to minimize ground contamination. Between 1955 to 1957, the NB-36H completed 47 test flights, accumulating hundreds of flight hours with an active reactor on board. These missions provided invaluable data on radiation exposure, shielding effectiveness, and structural integrity. The aircraft was escorted by support planes and followed strict safety protocols, including flight paths designed to avoid populated areas. Despite the precautions, the political and public sensitivity surrounding flying nuclear reactors was considerable. The program revealed that while nuclear propulsion was technically feasible, it posed enormous practical challenges. Shielding added excessive weight, reducing payload and performance. Any crash risk carried catastrophic consequences, and maintenance complexity was extreme. At the same time, advances in aerial refueling, jet engine efficiency, and intercontinental ballistic missiles reduced the strategic need for nuclear-powered aircraft. In 1957, the aircraft nuclear propulsion program was canceled, and the NB-36H was retired. The reactor was removed, and the aircraft was scrapped shortly thereafter. No nuclear-powered aircraft ever entered operational service. The NB-36H stands as a rare case where the United States built, flew, and then abandoned a technology not because it failed, but because its risks outweighed its benefits. It demonstrated that some Cold War ideas, once tested in reality, were simply too dangerous to pursue further. The KM Ekranoplan, Caspian Sea Monster, a 500-ton ground-effect giant with no doctrine. The KM Ekranoplan, better known in the West as the Caspian Sea Monster, was one of the largest and most unconventional vehicles ever to move under its own power. Developed by the Soviet Union during the height of the Cold War, the KM was an experimental ground effect vehicle designed to exploit the aerodynamic cushion formed when flying very close to the surface of water. Development began in the early 1960s at the Central Hydrofoil Design Bureau, led by chief designer Rostislav Alexeyev, a pioneer in high-speed marine and hybrid craft. The KM was completed and launched in 1966, immediately astonishing Western intelligence analysts when satellite imagery revealed a massive, aircraft-like shape skimming across the Caspian Sea. Measuring approximately 92 meters in length with a wingspan of around 37 meters, the vehicle had a maximum takeoff weight estimated at over 500 metric tons. It was powered by 10 Dobrin NVD-7 turbojet engines, mounted forward to blow air under the wings during takeoff and provide cruise thrust once airborne in ground effect. Unlike conventional aircraft, the KM was not designed to fly at altitude. It operated at heights of just a few meters above the water, where ground effect dramatically increased lift and reduced drag. This allowed the Ekranoplan to achieve high speeds while carrying enormous payloads, theoretically combining the advantages of ships and aircraft. Soviet planners envisioned roles including rapid troop transport, missile delivery, and surprise naval attack, exploiting the vehicle's ability to evade radar by flying below detection horizons. Despite its impressive performance, the KM was plagued by fundamental problems. Stability and control were difficult, particularly in rough seas, where wave height directly affected safe operation. The vehicle required calm or moderate sea states, severely limiting its usability. Navigation at high speed and extremely low altitude left little margin for error, and the Ekranoplan's size made emergency maneuvers slow and unforgiving. Most critically, the KM suffered from a lack of clear doctrine. It was neither a ship nor an aircraft, falling into an institutional gap between the Soviet Navy and Air Force. Each service questioned who should operate, maintain, and fund such a platform. Defensive survivability was also questionable, as the vehicle was large, lightly protected, and vulnerable to modern anti-ship weapons once detected. In 1980, after more than a decade of testing, the KM was lost in an accident during a repositioning flight. Pilot error during takeoff led to a crash into the Caspian Sea, and the enormous vehicle was never recovered. By that time, Soviet interest had already shifted toward smaller, more specialized Ekranoplans such as the Loon-class missile carrier. The Caspian Sea Monster was not abandoned because it failed to move or carry weight, but because it solved no clearly defined military problem. Without doctrine, infrastructure, or operational flexibility, the KM remained an engineering spectacle rather than a viable weapons system. It stands as a symbol of Cold War experimentation, pushed to colossal scale without a practical path to adoption. The Boeing YAL-1 airborne laser, a flying anti-missile weapon that arrived too late. The Boeing YAL-1 airborne laser was one of the most ambitious missile defense systems ever built, designed to destroy ballistic missiles in flight, using directed energy rather than conventional interceptors. The program originated during the 1990s, following decades of interest in laser-based missile defense dating back to the Strategic Defense Initiative of the 1980s. Its goal was to provide a mobile, reusable platform capable of intercepting enemy intercontinental ballistic missiles during their boost phase when they were most vulnerable. The system was built around a heavily modified Boeing 747-400F airframe chosen for its size, range, and electrical power capacity. The aircraft housed a megawatt-class chemical oxygen iodine laser, known as COIL, mounted in a large nose turret capable of precise tracking and beam control. Additional onboard lasers were used for target tracking, atmospheric compensation, and adaptive optics, allowing the main beam to remain focused over hundreds of kilometers. Development formally began in 1996 under the designation Airborne Laser Program, with Boeing as the prime contractor and major contributions from Northrop Grumman and Lockheed Martin. The aircraft was redesignated YAL-1A and first flew in 2002. Integrating the laser system required extensive structural modifications, including reinforced frames, chemical storage tanks, exhaust systems, and complex cooling infrastructure. The aircraft became one of the most sophisticated flying laboratories ever constructed. The YAL-1 achieved a major milestone on the 11th of February 2010 when it successfully destroyed a liquid-fueled ballistic missile during a test over the Pacific Ocean. A second intercept followed shortly afterward, demonstrating that laser boost phase missile defense was technically feasible. These tests validated decades of theoretical work and proved that a directed energy weapon could be used operationally against real missile targets. Despite its success, the program faced growing criticism. The aircraft had to operate relatively close to hostile territory to engage missiles during boost phase, placing it within range of enemy air defenses. The chemical laser required large quantities of hazardous fuel, limiting the number of engagements per mission and increasing logistical complexity. Each shot was expensive, and the aircraft's survivability in a contested environment was questionable. Strategic conditions also worked against the YAL-1. By the late 2000s, adversaries increasingly relied on solid-fueled missiles with shorter boost phases, reducing engagement windows. At the same time, ground-based interceptors and space-based sensors offered broader coverage at lower operational risk. Budget pressures further eroded political support for the program. In 2011, the U.S. Department of Defense canceled the Airborne Laser Program. The YAL-1 aircraft was retired and later dismantled, ending its operational life after only a handful of successful tests. The system was not abandoned because it failed, but because it arrived after the strategic environment had moved on. The Boeing YAL-1 remains a striking example of Cold War-era missile defense thinking carried into the modern age. It proved that airborne laser interception was possible, yet it also demonstrated that technical success alone does not guarantee strategic relevance. Project Orion battleship, the nuclear pulse, spacecraft that scared everyone. Project Orion was one of the most audacious spacecraft concepts ever seriously studied, proposing to propel massive vehicles through space using controlled nuclear explosions. The idea emerged in the late 1950s, during a period when nuclear technology was seen as a universal solution to engineering limits. Development began in 1958 under the direction of physicist Freeman Dyson, with major contributions from Theodore Taylor, Stanislaw Ulam, and other scientists working at General Atomics. The project was conducted with informal backing from the U.S. Air Force and later the Advanced Research Projects Agency. The basic principle of Orion was deceptively simple. The spacecraft would eject small nuclear charges behind itself, detonating them at precise intervals. Each explosion would strike a massive steel pusher plate at the rear of the vehicle, transferring momentum through a shock absorption system and producing thrust. Unlike chemical rockets, which are limited by fuel efficiency, Orion's performance scaled upward with size. The larger the spacecraft, the more efficient it became. Design studies envisioned vehicles of unprecedented scale. Early concepts proposed ships weighing thousands of tons, while later versions imagined interplanetary battleships exceeding several million tons. These spacecraft could theoretically carry crews of hundreds, large payloads, and extensive shielding. Performance estimates suggested Orion vehicles could reach Mars in weeks and travel to the outer planets with ease. Some designs even considered interstellar precursor missions. Technically, many challenges were addressed with surprising rigor. Engineers developed pusher plate materials capable of surviving repeated nuclear impacts, using graphite-based coatings to reduce erosion. Shock absorber systems were designed to smooth out the violent impulses into tolerable acceleration for human crews. From a purely engineering standpoint, Project Orion was considered feasible using 1950s technology. What ultimately doomed the project was not physics, but politics and fear. Launching Orion from Earth would require detonating hundreds of nuclear devices in the atmosphere, producing radioactive fallout on a global scale. Even space-based detonations raised serious concerns about contamination, weaponization of space, and escalation during an already tense nuclear standoff. The idea of routinely exploding nuclear bombs, even for peaceful purposes, was deeply unsettling to both policymakers and the public. In 1963, the Partial Test Ban Treaty prohibited nuclear explosions in the atmosphere, underwater, and in space. This single agreement effectively killed Project Orion overnight. Without legal ability to test or operate the propulsion system, the concept became politically impossible. Funding was withdrawn, and the project was formally abandoned in the mid-1960s. Project Orion remains unique in aerospace history. It was not a fantasy nor a fringe proposal, but a rigorously analyzed system that promised capabilities still unmatched today. It was abandoned not because it could not work, but because it worked too well in a world already terrified of nuclear power. Orion stands as the ultimate example of Cold War engineering colliding with ethical, environmental, and political reality. The German Landkreuzer P-1000 Ratte, a supertank built only to be cancelled immediately. The Landkreuzer P-1000 Ratte was one of the most extreme armored vehicle concepts ever seriously considered, embodying Nazi Germany's late war obsession with superweapons and overwhelming scale. The idea emerged in 1942, at a time when Germany faced increasing pressure on all fronts, and Adolf Hitler showed growing interest in gigantic prestige projects as symbols of technological dominance. The proposal originated within the Krupp armaments firm, which submitted preliminary studies for an armored vehicle so large that it defied conventional classification. The P-1000 Ratte was envisioned as a land battleship rather than a tank. Design concepts estimated a weight of approximately 1,000 metric tons, making it more than 10 times heavier than the Tiger II. The vehicle would have measured roughly 35 meters in length, 14 meters in width, and 11 meters in height. Its primary armament was to consist of a naval turret mounting two 280mm SKC-34 guns, the same weapons used on Scharnhorst-class battleships. Secondary armament included a 128mm anti-tank gun, multiple 20mm anti-aircraft cannons, and extensive machine gun coverage. Propulsion posed an immediate and nearly insurmountable problem. Early studies suggested using 2 Moen U-boat diesel engines or 8 Daimler-Benz marine engines, producing a combined output of several thousand horsepower. Even with this power, projected top speed was extremely low, and fuel consumption would have been enormous. The vehicle's weight would have made bridges impassable, roads unusable, and off-road movement nearly impossible. Transport by rail was entirely out of the question. Crew estimates ranged from 20 to over 40 personnel, requiring internal spaces more akin to a ship than an armored vehicle. Armor thickness was proposed to reach up to 360 millimeters in some areas, theoretically making the Ratte immune to most anti-tank weapons. In practice, however, its sheer size would have made it an ideal target for artillery, heavy bombers, and air attack. Concealment or rapid maneuver was impossible, and any battlefield deployment would have been slow and highly predictable. Despite these issues, Hitler reportedly approved further consideration of the project, reflecting his personal fascination with massive weapons. However, opposition emerged from within the German armaments leadership. In 1943, Armaments Minister Albert Speer intervened directly, recognizing that the Ratte would consume enormous resources better spent on conventional tanks, aircraft, and submarines. Germany's deteriorating strategic situation left no room for such extravagance. The P-1000 Ratte was cancelled before any physical construction began. No prototype was laid down, and the project existed only as drawings and conceptual studies. It was abandoned almost as soon as it was seriously examined. The Landkreuzer Ratte stands as a cautionary symbol of how ideology and spectacle can overwhelm practicality. It was not cancelled because it lacked firepower, but because it represented everything Germany could no longer afford. In the end, the supertank was defeated by reality before it ever left the drawing board. The Soviet Object 279, the 4-track apocalypse tank that had no future. The Soviet Object 279 was one of the most radical tank designs ever built, created at the height of Cold War fears that future battlefields would be dominated by nuclear weapons. Development began in the mid-1950s under the leadership of engineer Lev Troyanov at the Kirov plant in Leningrad as part of a Soviet program to explore next-generation heavy tanks capable of surviving nuclear blast effects, radiation, and extreme terrain. Unlike conceptual paper projects, Object 279 was fully constructed and tested, making its eventual abandonment particularly striking. The most distinctive feature of Object 279 was its 4-track running gear. Instead of the conventional 2 tracks, the tank used paired tracks on each side mounted to a complex suspension system. This configuration dramatically reduced ground pressure, allowing the vehicle to traverse snow, mud, swamps, and debris fields that would immobilize standard tanks. Soviet designers also believed the layout would improve stability against shockwaves from nearby nuclear detonations, reducing the risk of the vehicle being flipped or disabled. Equally unconventional was the hull design. Object 279 featured a cast, elliptical hull with pronounced curvature, resembling a flattened dome. This shape was intended to deflect blast waves and reduce the accumulation of radioactive dust following a nuclear explosion. Armor thickness reached up to 269 millimeters in critical areas, providing extreme protection against contemporary anti-tank weapons. The turret housed a 130mm M65 rifled gun, capable of defeating any Western tank of the period, supported by advanced stabilization and fire control systems for its time. The vehicle weighed approximately 60 metric tons and was powered by a 1,000-horsepower diesel engine, giving it a respectable top speed of around 55 kilometers per hour. On paper, Object 279 combined firepower, protection, and mobility at levels unmatched by any operational tank. However, this performance came at the cost of extreme mechanical complexity. The 4-track suspension was difficult to maintain, prone to failure, and required specialized support equipment. Field repairs would have been slow and impractical under combat conditions. Testing conducted between 1959 to 1960 revealed that while Object 279 performed well in controlled trials, it was ill-suited for mass production. Manufacturing the hull was expensive and time-consuming, and the running gear presented reliability concerns. More importantly, Soviet military doctrine was shifting rapidly. In 1960, Nikita Khrushchev formally de-emphasized heavy tanks in favor of missiles and lighter, more versatile armored vehicles. Nuclear war was increasingly seen as a missile-dominated conflict rather than one fought by super-heavy ground forces. As a result, Object 279 was canceled after only a single prototype was completed. It never entered service and had no direct successor. Today, the surviving prototype is preserved at the Kubinka Tank Museum. Object 279 was not abandoned because it failed to function, but because it belonged to a vision of war that vanished almost overnight. Designed for an apocalypse that never arrived, it had no future. Once doctrine, economics, and strategy moved on. The USS Long Beach, the first nuclear cruiser that proved too expensive to repeat. The USS Long Beach, CGN-9, was the world's first nuclear-powered surface combatant, representing a bold experiment in naval propulsion during the early Cold War. Conceived in the mid-1950s, the ship was intended to escort nuclear aircraft carriers and demonstrate that nuclear power could provide surface fleets with unmatched endurance and sustained high speed. The project emerged from U.S. Navy efforts to extend the success of nuclear propulsion beyond submarines, following the operational achievements of USS Nautilus. Construction began in 1957 at Bethlehem Steel's Quincy Shipyard, and Long Beach was commissioned in 1961. From the outset, Long Beach was a technological outlier. Powered by two C-1W pressurized water nuclear reactors, the ship could operate for years without refueling, limited primarily by crew endurance and maintenance rather than fuel supply. This capability made it uniquely suited for long deployments and rapid global response. At approximately 219 meters in length and displacing over 15,500 tons full load, Long Beach was large for a cruiser, reflecting the space required for reactors, shielding, and early missile systems. The ship's appearance was as unconventional as its propulsion. Long Beach featured a tall, slab-sided superstructure designed to house some of the earliest long-range naval radar arrays, including the AN/SPS-32 and SPS-33 phased array radars. These systems gave the cruiser advanced air search and tracking capabilities well ahead of their time. Its original armament included Talos and Terrier surface-to-air missiles, ASROC anti-submarine weapons, and later Harpoon anti-ship missiles, making it a multi-role escort platform. Operationally, Long Beach proved that nuclear-powered surface ships were feasible. It participated in deployments across the Atlantic and Pacific, and played a notable role during the Vietnam War, where its sensors and missiles contributed to fleet air defense. In 1964, Long Beach took part in Operation Sea Orbit, a high-profile, unrefueled global circumnavigation, alongside two other nuclear-powered ships, demonstrating the strategic reach of nuclear surface propulsion. Despite these successes, the ship revealed fundamental drawbacks. Construction costs were extraordinarily high, far exceeding those of conventionally powered cruisers. Maintenance of nuclear reactors required specialized infrastructure and highly trained personnel, increasing lifetime expenses. Advances in gas turbine propulsion, combined with underway replenishment at sea, reduced the operational advantages of nuclear power for surface combatants. By the 1970s, the U.S. Navy concluded that nuclear propulsion for cruisers offered diminishing returns. While later nuclear cruisers were built, none replicated Long Beach's experimental radar architecture, and the class was never expanded. Long Beach was decommissioned in 1995 and later scrapped, its reactors removed under strict controls. The USS Long Beach was not abandoned because it failed, but because it proved too expensive to serve as a model for the future. It demonstrated what was possible, then quietly confirmed what was impractical. The McDonnell XF-85, Goblin, a fighter built to live inside a bomber, then grounded forever. The McDonnell XF-85, Goblin was one of the most unusual fighter aircraft ever built, conceived during the final years of the Second World War, when long-range bomber survivability was a major strategic concern. Before the widespread adoption of aerial refueling, escort fighters lacked the range to accompany bombers deep into enemy territory. To solve this problem, the U.S. Army Air Forces proposed a parasite fighter that could be carried inside a bomber and deployed only when needed. McDonnell Aircraft was awarded the contract in 1945, producing a radically compact jet fighter designed to operate from within the bomb bay of a strategic bomber. The XF-85 was designed specifically to fit inside the bomb bay of the Convair B-36 Peacemaker. Measuring just 4.5 meters in length with a wingspan of 6.4 meters, it was far smaller than any operational fighter of its era. The aircraft was powered by a single Westinghouse J-34 turbojet engine and armed with 4.50 caliber machine guns mounted in the nose. Instead of conventional landing gear, the Goblin relied on a retractable trapeze system for launch and recovery, hooking onto a mechanism lowered from the bomber. The first flight of the XF-85 occurred on August 23, 1948, launched from a modified B-29 mothership rather than a B-36. While the aircraft proved it could fly, testing quickly revealed severe limitations. The Goblin's performance was inferior to contemporary fighters, with limited speed, range, and climb rate. Its small size left little room for fuel, reducing endurance to extremely short missions. Most critically, the recovery process was exceptionally difficult. Turbulence behind the bomber made it hard for pilots to align with the trapeze, and several attempts ended with failed hookups. During test flights, pilots struggled to dock the aircraft reliably. On multiple occasions, the XF-85 damaged its canopy and nose during recovery attempts, and 2 emergency belly landings were required. Although the aircraft itself survived, these incidents highlighted the operational risks. Even under controlled test conditions, docking was dangerous. In combat, with evasive maneuvers, enemy fire, and weather effects, successful recovery was highly doubtful. By the late 1940s, the strategic environment had changed rapidly. Aerial refueling techniques improved, allowing escort fighters to accompany bombers over long distances. At the same time, jet fighter performance advanced so quickly that the Goblin was already obsolete before it could mature. Carrying a parasite fighter also reduced the bomber's payload and added complexity without guaranteeing protection. In 1949, the XF-85 program was formally canceled after only 2 prototypes were built. Neither aircraft entered service. One survives today in the National Museum of the United States Air Force. The XF-85. Goblin was abandoned not because it could not fly, but because it represented a solution overtaken by better ideas. It remains a striking reminder of how quickly Cold War aviation concepts could be rendered obsolete by technological progress.